There is nothing. Not darkness. That would imply the absence of light. There is no absence because there is no presence, no space for darkness to occupy, no time for silence to pass through. And then, something. Not an explosion, that word is wrong, it was more like a thought. The first thought anything ever had. In a span of time so small that no human language has a word for it, a trillionth of a trillionth of a trillionth of a second, everything that would ever exist began to unfold. This is the story of all of it. Every star, every atom in your body, every breath you have ever taken, it all starts here, in a space smaller than a full stop on this screen. Close your eyes if you like. This story has been waiting 13.8 billion years to be told. It can wait a little longer for you to get comfortable. The universe, in its first moments, was not a place you could visit. It was smaller than an atom and hotter than anything that has existed since. The temperature, and this number is real, was 10,000 trillion degrees, a number so large that writing it out would fill this entire screen with zeros. At this temperature, the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force and the weak nuclear force, were indistinguishable. They were one single force, one rule governing everything. Within the first second, this unity shattered. Gravity separated first, pulling away like a thread from a tapestry. Then the strong force. Then the electromagnetic and weak forces split from each other. Each separation released energy. Each release of energy created particles. Quarks appeared, the smallest building blocks of matter. They collided and combined, forming protons and neutrons. All of this happened before the universe was 3 minutes old. By the time those 3 minutes had passed, the universe had already decided the ratio of hydrogen to helium that would define every star that would ever burn. Roughly 75% hydrogen, 25% helium, a trace of lithium. That ratio has not changed in 13.8 billion years. The ingredients were set in the first 3 minutes, and the universe has been cooking with them ever since. But here is the part that deserves a moment of quiet appreciation. The universe could have got this wrong. If the balance between matter and antimatter had been even slightly different, by 1 part in a billion, everything would have annihilated itself. Matter and antimatter would have met, cancelled each other out, and there would be nothing left. No atoms, no stars, no planets, no you. But for every billion antimatter particles, there were 1,000,000,001 matter particles. That extra one, that impossible, improbable, inexplicable one, is the reason everything exists. You're here because of a rounding error in the first second of time. After the fury of the first few minutes, something unexpected happened. Nothing. For 400 million years, the universe went dark. Cosmologists call this the Dark Age, and it is exactly what it sounds like. No stars, no galaxies, no light of any kind. The universe was filled with a fog of hydrogen and helium atoms, a vast, warm, featureless cloud stretching in every direction. Light could not travel through it. If you were somehow there, floating in this cloud, you would see nothing. Absolute, total, impenetrable darkness. But the cloud was not still. Gravity was working. Slowly, over millions of years, the cloud was developing texture. Slightly denser regions were pulling atoms towards them. Very gradually, the uniform fog was developing lumps. Think of it like this. Imagine a perfectly flat lake. Then imagine the faintest possible breeze touching its surface. The ripples are so small you can barely see them, but given enough time, those ripples become waves. That is what was happening. The universe was developing structure. The seeds of every galaxy, every star, every planet, including ours, were being planted in this silence. And nobody was there to see it. No consciousness anywhere in existence. Just physics, doing what physics does, in absolute darkness, for longer than human civilization has existed multiplied by 100,000. There is something oddly peaceful about that. 400 million years of quiet. The universe taking its time. No rush, no purpose. Just the slow, patient work of gravity gathering dust. And then, in one region of space, no more special than any other, the density crossed a threshold. And the first star ignited. The first stars were monsters. We call them Population 3 stars, a name that sounds clinical, but the reality was anything but. These stars were hundreds of times more massive than our Sun. Some were 1,000 times more massive. They burned with a ferocity that made them millions of times more luminous. And they burned fast. A star like our Sun will last 10 billion years. These first stars lasted perhaps 2 million years, some even less. In cosmic terms, they were lit matches, brilliant and brief. But in those brief lives, they did something extraordinary. Inside their cores, hydrogen was being crushed into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron. Layer by layer, element by element, these stars were forging the periodic table. Every element heavier than hydrogen and helium was made inside a star. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was cooked in the heart of a star that died billions of years before our Sun was born. And when these first massive stars died, they did not go quietly. They exploded. Supernovae, the most violent events in the universe. A single supernova for a few weeks can outshine an entire galaxy of 100 billion stars. The energy released is more than our Sun will produce in its entire 10 billion year lifetime. These explosions scattered the newly forged elements across space. Carbon, oxygen, nitrogen, iron, flung outward at a significant fraction of the speed of light, seeding the universe with the raw materials for everything that would come next. Planets, oceans, amino acids, DNA, you. The astronomer Carl Sagan said it simply, "We are star stuff," and he meant it literally. There is not a single atom in your body that was not once inside a star. Take a breath. Feel your lungs expand. That oxygen was forged at 100 million degrees in a stellar core that no longer exists, in a galaxy that may no longer exist, in an era of the universe that ended billions of years ago. And it found its way to you. Once the first stars had lived and died and scattered their elements, the universe entered a new phase. Gravity, still working with infinite patience, began pulling matter together on an even larger scale. Not just individual stars now, but vast collections of stars, hundreds of billions of them, drawn together into rotating disks and ellipses and irregular clouds. Galaxies. The first galaxies were small and chaotic, irregular blobs of a few billion stars crashing into each other, merging, growing. Galaxy formation was not a gentle process. It was violent, messy, and took billions of years. But gradually order emerged from the chaos. The collisions slowed. The mergers produced larger, more stable structures. Spiral arms formed, not because anything designed them, but because the mathematics of rotation and gravity naturally produce spirals. The same mathematics that make water spiral down a drain, or a hurricane spin into a disk. Spirals are what happens when things rotate and gravity pulls. The universe was not designed to be beautiful. Beauty is simply what physics looks like when you give it enough time. By roughly 1 billion years after the beginning, the universe was populated with billions of galaxies, each containing billions of stars, each star potentially surrounded by planets. The numbers become difficult to hold in your mind. There are more stars in the observable universe than grains of sand on every beach on Earth, and each of those stars is a sun, many of them larger than ours, many of them older. And between them, the vast, cold, silent spaces. Light takes 100,000 years to cross a single galaxy. It takes 2.5 million years to travel from the nearest large galaxy, Andromeda, to ours. The universe is not just big. It is big in a way that the human brain was never evolved to comprehend. We can say the numbers, we can write the equations, but we cannot feel them. Our minds evolved to navigate African savannas, not intergalactic voids. And yet here we are, trying anyway, which is rather wonderful when you think about it. Billions of galaxies forming across the universe, one was quietly assembling itself in an unremarkable corner of space. The Milky Way, our home. It began as most galaxies did, a series of smaller galaxies merging together over billions of years. Astronomers have identified at least 24 smaller galaxies that the Milky Way has absorbed over its lifetime. Their stars now orbit among ours, indistinguishable, fully assimilated. Today, the Milky Way contains somewhere between 100 billion and 400 billion stars. The uncertainty in that number, a margin of 300 billion stars, tells you something about how much we still do not know. It is approximately 100,000 light-years across. To cross it at the speed of light, the fastest speed possible, would take you 100,000 years. In a commercial aeroplane, it would take roughly 120 billion years, longer than the universe has existed. At the centre of the Milky Way sits a supermassive black hole. It is called Sagittarius A, and it contains the mass of 4 million suns compressed into a region smaller than our solar system. Nothing that crosses its event horizon will ever return. Not matter, not light, not information. It is, in every meaningful sense, a boundary beyond which the universe stops being the universe. And yet, paradoxically, this black hole is what holds the galaxy together. Its gravity anchors the orbits of billions of stars, including our Sun, which is currently circling the galactic centre at 828,000 kilometers per hour. You do not feel this speed. You never have. You are right now moving through space at nearly 1 million kilometers per hour, and it feels like lying still. The Milky Way has been spinning for roughly 13 billion years. In that time, our solar system has completed perhaps 20 full orbits. Each orbit takes about 230 million years. The last time we were in this exact position in the galaxy, dinosaurs had just begun to appear on Earth. About 4.6 billion years ago, in an unremarkable arm of the Milky Way, a cloud of gas and dust began to collapse. This was not unusual. Clouds like this collapse all the time across the galaxy. What made this one matter is simply that we are here to talk about it. The collapse was probably triggered by a nearby supernova, the shockwave from a dying star compressing the cloud just enough to start the chain reaction of gravity. Poetic in a way, a death creating the conditions for a birth. As the cloud collapsed, it began to spin, faster and faster, like an ice skater pulling in their arms. The centre grew dense and hot. The outer material flattened into a disk. When the temperature at the centre reached about 15 million degrees, hydrogen atoms began fusing into helium. Nuclear fusion ignited. Light poured out for the first time. Our sun was born. It was not a dramatic event on the cosmic scale. Millions of stars were being born in the galaxy at the same time. Ours was average in size, average in luminosity, average in temperature, a perfectly ordinary yellow dwarf star. And that ordinariness is precisely what makes it perfect for life. Larger stars burn too fast. They exhaust their fuel in millions of years. Not enough time for complex chemistry to develop on any planets orbiting them. Smaller stars are too dim and too prone to violent flares. Our sun sits in a narrow band of stellar properties that astronomers call the main sequence sweet spot. Not too big, not too small, not too hot, not too cold. Stable enough to burn for 10 billion years. It is now roughly halfway through its life. It has about 5 billion years of fuel remaining. When it exhausts that fuel, it will swell into a red giant, large enough to engulf Mercury, Venus, and possibly Earth, before collapsing into a white dwarf. But that is a story for another night. For now, the sun is steady. It has been steady for longer than complex life has existed on Earth, and it will remain steady for longer than complex life is likely to survive. disk of material orbiting the newborn Sun, something was happening at roughly 150 million kilometers from the center. Grains of dust were sticking together. Pebbles were colliding to form boulders. Boulders were merging into planetesimals, bodies a few kilometers across, and these planetesimals, through millions of years of collisions, were building a planet. Earth. The process was extraordinarily violent. The early Earth was a molten sphere, its surface a churning ocean of liquid rock. The temperature was thousands of degrees. The atmosphere, if you could call it that, was a toxic brew of carbon dioxide, methane, and ammonia. There was no oxygen, no water on the surface, no oceans, nothing that any living thing today would recognize as home. But Earth had something going for it. It was the right distance from the Sun, in what astronomers call the habitable zone, or more poetically, the Goldilocks zone. Not too hot for water to evaporate, not too cold for it to freeze permanently. Of course, there was no liquid water yet. That would come later. But the conditions were right. The potential was there. Earth also had the right mass, large enough for its gravity to hold an atmosphere, small enough that it did not become a gas giant, large enough for a liquid iron core which would generate a magnetic field, and that magnetic field would later prove essential for life, shielding the surface from the Sun's radiation. Everything was falling into place, not by design, not by plan, just by the patient, impersonal arithmetic of physics and gravity. And then something happened that no one expected. About 4.5 billion years ago, only 50 million years after Earth formed, a body the size of Mars struck our planet. The collision was beyond anything the human mind can visualize. The impactor, which astronomers have named Theia, hit Earth at roughly 40,000 kilometers per hour. The energy released was equivalent to trillions of nuclear weapons detonating simultaneously. Earth's surface was completely liquefied. The crust, which had only just begun to solidify, was obliterated. Vast quantities of rock and metal were blasted into orbit. This debris, a ring of molten rock encircling the wounded Earth, coalesced over the following centuries into a new body. The Moon. It is an extraordinary origin story. Our moon, the same moon you can see from your window, was born from a catastrophic collision that nearly destroyed our planet before it had a chance to begin. But the moon did more than just appear. It stabilized Earth's axial tilt, preventing the wild wobbles that would otherwise make seasons chaotic and climate unpredictable. It created tides, which would later play a role in the transition from ocean life to land life. The worst thing that ever happened to early Earth turned out to be one of the most important things that ever happened to life. Destruction and creation. Again and again, the universe makes no distinction between the two. Hundreds of millions of years after the moon-forming impact, Earth was bombarded. The inner solar system was still full of debris, asteroids, comets, planetesimals that had not yet been swept up by the gravity of the major planets. They rained down on Earth, on the Moon, on Mars, on Venus. This period is called the Late Heavy Bombardment, and it lasted from roughly 4.1 to 3.8 billion years ago. But these impactors were not just agents of destruction. Many of them carried water, trapped as ice within their rocky bodies. Comets, in particular, are essentially dirty snowballs, rock and dust held together by frozen water, carbon dioxide and methane. Each impact delivered water to the surface. Not much per impact, but over hundreds of millions of years, the cumulative effect was transformative. The Earth's surface, which had cooled enough for a solid crust to form, began to accumulate liquid water. First in small pools, then in lakes, then in seas, and eventually, around 3.8 billion years ago, the first true oceans appeared. This is one of the most remarkable transitions in the history of the planet. From a molten hellscape bombarded by asteroids to a world covered in liquid water, in just a few 100 million years. And with water came chemistry, dissolved minerals, thermal gradients, chemical reactions that would have been impossible on a dry world. The stage was being set. Not for life, not yet, but for the conditions in which life could begin. Somewhere on Earth, roughly 3.7 to 3.8 billion years ago, chemistry became biology. We do not know exactly how. This is one of the deepest unsolved questions in all of science. We know what was there before: complex organic molecules, warm mineral-rich water, energy sources like hydrothermal vents and ultraviolet light. And we know what appeared after: self-replicating molecules, the first protocells. But the precise moment of transition, the moment when a collection of chemicals first copied itself, remains unknown. What we do know is that it happened quickly in geological terms. Earth became habitable around 3.9 billion years ago. The earliest evidence of life dates to about 3.7 billion years ago. That is a window of just 200 million years, short by cosmic standards. This suggests that life, given the right conditions, may arise readily. It may not be a cosmic miracle, it may be a cosmic inevitability, something that happens wherever water, carbon and energy coexist for long enough. Or it may have been a 1 in a trillion fluke that happened to occur here. We genuinely do not know. We have a sample size of 1. What we do know is that the first organisms were simple, single-celled, probably similar to modern archaea, tough, resilient organisms that thrive in extreme conditions. They lived in the ocean, near hydrothermal vents, feeding on chemical energy. For the next 2 billion years, this is all life was. Single cells in the sea, no plants, no animals, no eyes, no brains, no movement. "2 billion years. Try to hold that number for a moment. 2 billion years of nothing but microbes. Human civilization is roughly 10,000 years old. Multiply that by 200,000, and you begin to approach the timescale during which the most complex thing on Earth was a single-celled organism. Patience. The universe has always been patient. And then, in the last fraction of a percent of Earth's history, as everything accelerated. Complex multicellular life appeared roughly 600 million years ago. Fish evolved 500 million years ago. Plants colonized the land 470 million years ago. Insects 400 million. Reptiles 300 million. Dinosaurs 230 million. The dinosaurs ruled for 165 million years, 800 times longer than humans have existed. They were not the failures popular culture sometimes portrays them as. They were one of the most successful groups of organisms the planet has ever produced. They ended not because of any failing of their own, but because a 10-kilometer wide asteroid happened to hit the Yucatan Peninsula 66 million years ago. Bad luck on a cosmic scale. In the aftermath, small mammals, our distant ancestors, found themselves in a world suddenly emptied of giant predators. They diversified, they grew larger, they developed bigger brains. About 300,000 years ago, Homo sapiens appeared in Africa, a species with an unusually large brain relative to its body size, a species that could make tools, use language, plan for the future, and uniquely wonder about its own origins. For the first time in 13.8 billion years, the universe had produced something that could look back at it and ask, how did all of this happen? You are that, right now. Lying in the dark, listening to this voice, you are the universe examining itself. The hydrogen that formed in the first 3 minutes of existence has been rearranged through star formation, supernova explosions, planetary accretion, chemical evolution, and biological evolution into a brain that is capable of understanding the story of its own creation. That is not poetry. It is physics. Every atom in your body can be traced to a specific process in the history of the universe. You're not separate from the cosmos. You are the cosmos, doing something it has never done before. The universe is 13.8 billion years old, but it is not finished. In 5 billion years, the Sun will exhaust its hydrogen fuel and swell into a red giant. Earth will likely be engulfed or rendered uninhabitable. But by then, if we survive, we will have had 5 billion years to figure out what to do about it. The universe itself will continue for far longer than that. Stars will continue forming for another 100 trillion years. After that, the last stars will burn out, and the universe will enter a long, cold era of darkness. Black holes will slowly evaporate over timescales that make the current age of the universe look like a single heartbeat. The last black hole will evaporate roughly 10 to the power of 100 years from now, a 1 followed by 100 zeros. And after that, there will be nothing left but a thin, cold soup of subatomic particles, drifting apart in an ever-expanding void. No stars, no light, no structure, no change. This is the most likely fate of the universe. Not a dramatic end, but a slow, quiet fading. The technical term is heat death. Everything reaches the same temperature. Nothing interesting can ever happen again. But that is unimaginably far in the future. Right now, we're in the golden age of the cosmos. Stars are burning, galaxies are spinning, planets are forming, life is evolving. Right now, the universe is alive with possibility, and you are part of it. just heard the story of 13.8 billion years. Every atom of it is true, every star that burned, every galaxy that formed, every molecule of water that fell on the early Earth, all of it happened, all of it led to this moment. To you, here, now, warm, safe, breathing. The universe is not finished telling its story, but for tonight, this is enough. Close your eyes, let the stars continue their work without you for a while. They will still be there in the morning,